Polar coordinates are almost like the native language of complex analysis. It is hard to have a conceptual grasp of physical problems without them. This is particularly true in the realm of physics. By separating the number into polar coordinates, we are separating the number into a scaling part and a rotational part. Ideas that will be essential when we do multiplication in the next video. In this video, we're going to introduce one of the most famous formulas in all of mathematics, Euler's identity. Additionally, we're going to improve our visualization tools by introducing enhanced phase portraits. We will use these tools to start exploring more complex functions. Begin. So far we have represented complex numbers in Cartesian form. For example, z equals a plus bi. Where a is the real part, and b is the imaginary part. However, it is also possible to represent a complex number in polar form. For this we use two values which we will call r and theta for now. R is the radius, and theta is the angle from the positive real axis. R is the radius of our point. R is the absolute value of z, which we can write like this. Often call it the modulus or mod z, which is why we call our 3D phase portrait modular surfaces. Mod z can be calculated from the Cartesian form using Pythagoras' theorem. R equals the square root of a squared plus b squared. Theta is the angle of our point. It is always measured anti-clockwise from the positive real axis. This value is quite important in complex analysis, so we give it a special name. It is called the argument, which we will write with a special function, theta equals argz. To convert from Cartesian form, we can calculate theta using standard trigonometry. Theta equals the arctan of b over a. However, remember that the inverse tan function on your calculator doesn't always give you the result in the correct quadrant. If the real component is 0 or negative, you'll need to adjust theta appropriately. If you are using a computer, just use the atan2 function. Theta equals atan2, comma a. This function will give you the result in the correct quadrant automatically. Usually, we constrain theta to be between plus or minus pi. This isn't always the case, as we will see later. Visually, we can now draw a complex plane like this, showing lines of equal radius. It is still the same complex plane that we know and love, but sometimes it is easier to view it with a polar grid. How do we actually write down numbers in polar form? There are actually 4 reasonably common ways to represent our point z in polar form, using the values r and theta. Firstly, the angle form. R equals angle sine theta. It is sometimes used as shorthand in some engineering fields, and it's quite uncommon in pure mathematics. Secondly, the full trigonometric form, z equals r times cos theta plus I sine theta. This form is a little cumbersome, but it has the advantage of explicitly showing the underlying mathematics. Cis form is a shorthand way of writing the trigonometric form, z equals r cis theta. A cis stands for cos plus I sine. All of the above forms are useful because you can measure theta in degrees or radians. Just make sure your calculator is set appropriately. The fourth form, however, the exponential form. It is by far the most widely used. It is also the most useful. However, theta must be expressed in radians to use this form. We will be using the exponential form in most of this video series, but take a moment to memorize it. Z equals r times e to the power of I theta. The exponential form may be very surprising at first. E is Euler's number, famous from calculus. Exponential e to the x is the only function in mathematics whose derivative is equal to itself. Because we're now using radians instead of degrees for angles, Let's quickly recap what a radian is, just in case you've forgotten. Additionally, we have measured angles in degrees. Dates back thousands of years to Babylonian times. The Babylonians counted in groups of 60, and by convention we make a full circle 360 degrees. The choice of 360 is quite arbitrary, popular, because it divides into whole numbers very easily. However, there is a far more natural choice. This choice is used commonly in mathematics and the sciences. Why don't we instead let the angle that makes the whole circle be equal to its circumference? A unit circle, that is a circle of radius 1, has a circumference of 2 pi. So we'll make an angle of 360 degrees equal to 2 pi radians. Now, any smaller angle has a side in radians equal to the length around its arc. For example, if you are asked to walk 90 degrees around the outside of a radius 1 circle, distance you would have travelled would be pi on 2. So we say that the angle is pi on 2 radians. To convert between degrees and radians, simply use a full circle of each measurement as a ratio. A circle has 360 degrees, or 2 pi radians. So multiply by 360 over 2 pi to convert from radians to degrees. Or multiply by 2 pi over 360 to convert from degrees to radians. Quite a bit of information to take in here. Let's take a step back and look at some simple complex numbers in polar form. Minus 1 equals e to the I pi. Modulus is 1, and the angle is pi radians. Minus 5 equals 5 e to the I pi. I is equal to e to the I pi over 2. Minus I is equal to e to the minus I times pi over 2. 1 minus I is equal to the square root of 2, e to the minus I times pi on 4. Of course, I'm choosing numbers here that have an exact conversion. Normally that isn't the case, and the conversions can look quite ugly. Don't worry, in most applications we just always work in the most convenient form. In physics, this is pretty much always the polar form, as it gives us a nice separation between the magnitude and the angle. We will dedicate a whole video later in this series to explore the exponential function in detail, because it is just so fascinating. But for now, I'll quickly introduce Euler's famous discovery, which is one of the most famous equations in all of mathematics. It's known as Euler's identity. E to the I theta equals cos of theta plus I sin theta. Well before most mathematicians were taking complex numbers seriously, Euler discovered that the complex numbers can directly link the exponential and trigonometric functions. Did this by expanding the exponential sine and cosine functions out into their corresponding Taylor series. A Taylor series is an infinite polynomial that is equal to the function. If you look at these series very closely, you can see that e to the x has all the powers of x. The cosine function has all the even powers, and the sine function has all the odd powers. Otherwise, they look closely related. Wouldn't it be nice if we could add the sine and cosines together to make the exponential function? The signs of the individual terms aren't quite right, however. What Euler realized was that you can substitute in I theta for x and multiply the sine function by I. Consequently, Euler's identity really legitimized the idea of complex numbers. It links several seemingly unrelated parts of mathematics together. Also makes calculations involving trigonometry much easier, because we're quite good at manipulating exponentials using standard algebra. However, math YouTubers, like myself, To plug in theta equals pi radians into this equation, show this elegant and astonishing result. E to the I pi equals -1. This function contains three of mathematics' great constants, smushed together into one simple equation. In summary, polar form of our complex numbers will henceforth be written as z equals r times e to the power of I theta. R, the radius, is the distance from our origin, or mod z. Theta is the angle measured anti-clockwise from the real axis, or arc z. Theta is always measured in radians when we are using the exponential form. This is the phase portrait f of z equals z. Color on the graph shows the argument of the function, or arc z. 2D phase portrait does not show the value of mod z, or r. If we wanted to see the absolute value of z, we can create contour lines on our phase portrait by varying the lightness of the color. We do this in such a way that it shows up as steps, or contour lines. Each contour line that you currently see represents an increase in the absolute value of 1. For our function f of z equals z, they are simply the lines of equal radius that we saw earlier. It's also possible to add lines of equal angle. Correspond exactly to the color, so in theory, they're not needed. However, our perception of color is not perfect, and it is often influenced by nearby colors. So it is very often useful to add these color lines. These lines show parts of the function where arc of z is equal. We call this graphic an enhanced phase. Notice that the lines of contour and angle always cross at right angles. The enhanced phase portrait for cos of z looks like this. The lines still cross at right angles. Our phase portrait now has a sense of scale that was previously lacking in 2D. If I want to, I can isolate the contour lines, or lines of equal argument. The spacing between these lines is quite arbitrary though. We can change the size of the contour to suit. For example, if we zoom out, bigger steps are more readable. If we zoom in, smaller steps can be useful. For our enhanced phase portraits, we'll adjust our graphics as required. For now, I'll change our contour size back to 1, and I'll divide our angle into 16 lines. What we can do now is add some different constants to cos of z, and see how our phase portrait reacts. Once I start the animation, pause the video, and see if you can pick out the points that are equal to 0. Then, try and pick out the areas where the absolute value is equal to 1. And use color to determine the approximate argument of the output. Okay, let's begin. Just pause the video as required. If you'd like to explore these ideas further, I'll upload a series of extra visuals exploring the phase portraits of the trigonometric functions. Check the links in the description of this video. We don't really need contour lines in 3D. because we represent the absolute value as height. But that doesn't mean that they're not useful on occasion. Contour lines on a modular surface are lines of equal height. Though we can see our lines clearly, I'm going to adjust our graphic from class to something a little non-metallic. Now I'll add the contour lines as a texture, so we can read off the values easily. Means that the lines are sometimes stretched in flat areas and condensed in the steeper parts. The real and imaginary axes are also included for your reference. Axes cross the contour lines are right angles. Let's fly around the function. Time is zoomed. Can see that lines of equal radius become a wall with almost straight lines towards the imaginary inputs. We shall see in future videos. This is a trait of the exponential functions, the make-up cause of Z. For some functions, such as tan of Z, texture looks quite ugly as the imaginary parts all approach an absolute value of 1, so I probably won't use the texture too often. We can see almost all of the important information of the function tan of Z by inspecting the shape. We can see that there are zeros where it touches the base, and we can see simple poles where the function shoots off towards infinity. So that's it for this video. We have found the polar form, also known as the exponential form of a complex number. Using the polar form will start to feel quite natural, as it allows us to express a number directly in terms of size and rotation. In the next video we will investigate multiplication. What we will find is that we can use multiplication to scale and rotate functions.